Okay, so now we are doing problem 11-2. Okay, so we are given this diagram here, and we know that a uniform magnetic field of magnitude B is horizontal and directed into the page in a rectangular region of space shown in your diagram. A light, rigid wire loop with one side of width L has current I. The loop is supported by a magnetic field and it hangs vertically. The wire has resistance R and supports a box that holds a battery to which the wire loop is connected. The total mass of the box and its contents is capital M. Okay, part A. So you are given a diagram that looks like this. And it is your wire loop with your M mass hanging at the end, like that. And you are supposed to denote the direction of the current I. So in order to do this, we can use the right-hand rule. Now, first of all, we know that the current is the magnitude B is directed into the page as shown by the diagram and by the directions. So we're going to use a right-hand rule in which my thumb is going to represent the direction of B, and the way that my fingers curl is going to represent the direction of the current. So now if we direct my magnetic field into the page, we see that my fingers are curling in a clockwise direction. So that's going to be the direction of current I. So on your diagram, it's going to look like this. It's going to be going this way. Okay, part B. The loop remains at rest in terms of any or all of the quantities B, L, M, R, and appropriate constants. Determine expressions for the current I in the loop. Okay, so we know that because the wire loop is being held vertically, like this, we know that there is going to be a magnetic force on it because it's in a magnetic field, but there's also going to be a force from gravity, which is indicated in the diagram as mg. Now, because this wire loop isn't moving anywhere, we know that these forces must be equal to each other. So we know that F magnetic, which is F sub B, is equal to F sub G, which is the force from gravity. Now, how can we use this to solve for I? Because that's what the question is asking you for. So, one of the expressions for I, or for F, is that it is equal to the integral of I dl cross B. And of course, Fg is equal to mg as indicated in the diagram. So, first of all, we have to get rid of this cross product here in order to evaluate. So we know that this current is directed into the page, but that the current is going to be clockwise. So you have this directed into the page, but the current is actually going to be going clockwise in this vertical way, because that's the way that the wire is being held. So we know that these values are perpendicular. So we can get rid of the cross product, and now we would just multiply. So we have I and B are constants, so taken out of the integral, unchanged. And dl, the integral of that, is just going to be L. So IBL is equivalent to mg. And now we can just solve for I. mg over L. Part C. Now we have to solve for the EMF of the battery, assuming that it has negligible internal resistance. So in order to do this, we are given R in the problem, and we've just solved for I in the previous part. So we can really easily use Ohm's law, which is V equals IR. So what we do is we plug in our expression for I, mg over LB times R, and that's all that one is. Now, part D. An amount of mass delta M is removed from the box and the loop then moves upward, reaching a terminal speed V in a very short time before the box reaches the field region. In terms of V and any or all of the original variables, we have to, first of all, determine the magnitude of the induced EMF. So we know that the equation for E induced equals negative d flux over dt. Okay, so how do we find the derivative of flux? So another equation we can use is that flux is equal to the integral of B, magnetic field, dot dA. Now, in this case, we are fortunate in that the magnetic field and the area are parallel to one another, so this dot product, we can take that out of the equation. So now we have B times the integral of dA, which is just going to be A. Now, if we look at our original diagram, we had a rectangle of wire, and the length is given, or the width is given as L. And now I'm going to designate this side as having a length of X. So now the area of this rectangle is going to be equal to BLX. So now we have an equation for flux that we can now substitute back into our equation for induced EMF. So E induced equals negative d over dt of BLX. Now B and L are not going to be changing over time, so we can take that out of the way when we are taking the derivative. However, we do have X changing with time because the wire is moving upwards. So dx dt is an alternative way of saying V, which we are given. So now we know that E induced equals negative BLV. Okay, next part. Now we need to find the current I naught in the loop under these new conditions. Okay. So as before, we know that the relationship between V and I is through Ohm's law. V equals IR. We are solving for current, so now we can modify that equation into I equals V over R. Now, we have to figure now in this case this is I prime. Now the voltage that we're going to use here is going to change because we have to deal with the induced EMF. So as the wire is moving up the magnetic field, the flux is actually increasing. And so because of Lenz's law, in order to balance that effect, the induced EMF is going to take away from the original EMF. So our new expression for V, now that we have this new change taking place, is the original EMF minus the induced EMF over R, which has not changed. Now we can plug in the values we already have for our EMFs. I prime equals mgr over LV was our original, minus BLV, and that's times 1 over R. Okay, our last part is part F, and now we are finally being asked to solve for the amount of mass delta M that was actually removed. So, Now we can go back to our original relationship that we found between the equivalence of magnetic force and gravitational force. Now we know that FB is going to be equal to integral of I dl cross B. And then Fg equals the mass times G. Now, because we know that a certain amount of mass delta M was removed from our original M, we know that the mass we are now looking at, the adjusted mass, is going to be our original M minus delta M, which was taken away, times G. Now we can simplify this expression as we did before, except because we're dealing with the new conditions, the I is going to be I prime. So I prime LB equals M minus delta M G. Now we are solving for delta M. And this requires rather a lot of algebra because you have to sub in for I prime. So let's see how we can condense this. M minus delta M, I'm going to switch the sides here to make it easier, is equal to our solution from the previous problem. Mg over Lb minus BLV over R times BL. Now just as a note, I already multiplied in the 1 over R from the previous problem. So that's already taken care of. So now we have to do some more algebra. So we're going to end up with BL times MGR over B squared L squared B, because we're doing a common denominator of BLR. Now we can cancel, and we can also divide by G. Okay, and now we can add M. Okay, so now what you'll notice is that if you split up this huge fraction, you're going to end up with M, because this GR over RG is going to cancel in this case, minus I'm sorry, these signs are actually switched because this is a minus M in the initial case. So now that the signs are right, we're going to end up with minus M plus B squared L squared V over GR plus M. Now we can cancel, these add up to 0, and we know that delta M, B squared L squared V over GR.